Welcome to Physics 4B, and welcome to this first lecture video for Physics 4B. This second semester course on calculus-based general physics is the course that covers thermodynamics, electricity, and magnetism here at College of Alameda. We will start our semester with thermodynamics and spend most of the semester with electricity, magnetism, and circuits. As we start this semester, let me use this first lecture to do a short mechanics review. The main focus of this mechanics review is on problem-solving techniques you learned in Physics 4A. So we will spend nearly all of the time in this lecture doing that. But let me demonstrate something that may be useful to some people who need a more thorough review than a simple reminder of what you learned last semester. Something that could be used as a just-in-time review. So, this is a screenshot from our last lecture for Physics 4A, recapping the mechanics semester. If every expression here holds some meaning for you, then great! You are in good shape as far as any review needs go. If, as you are looking at this, if you feel lost, unsure what some of the weird-looking symbols even are, what do you do? In the past, I would have advised you to do one of two things. One, ignore these for now, but as you proceed, set aside enough time so that as you study the 4B topics, you can go back to the necessary parts of 4A as needed. If you thought you could handle 20 units of coursework for the semester, only take 15 units or less. Or two, set aside enough time, like 2 to 3 months, to study and review mechanics. Now, depending on when you are watching this video, the second option may not be much of an option, leaving you with the first option, which I think many students do anyway, and most of them do fine. Today, you have one more option. Ask ChatGPT for an interactive review. Let me demonstrate. So I'm going to take a screenshot of this screen, and I have ChatGPT open on my second tab. Let me show you what kind of questions you could ask ChatGPT that it would help you with your interactive review of mechanics as you prepare for this semester on thermodynamics, electricity, and magnetism. In fact, I'll just spell that out. Let me paste in the image so that ChatGPT has a context. Hi, I'm preparing to start a new semester of calculus-based general physics class covering thermodynamics, electricity, and magnetism. And I think I've forgotten everything they covered in the previous class. I have this screenshot of the recap lecture that the instructor did last semester, but much of what's in the screenshot doesn't make sense to me. Can you help me spot the things I need to review in preparation for the new semester? And the kind of things that ChatGPT points out might be something that I could have done if we had a real-time, in-person lecture session that we don't for our 100% asynchronous online class. And it knows it's a Physics 4A either from the image or because it has past memories of me interacting with it on a 4A material. Yeah, roadmap it to the colored boxes and arrows. Okay, use it as a checklist. Heading feels hazy. That's the spot to revisit before plunging into thermodynamics and ENM. Yeah. So blue red box, bottom right. Ah, interesting. It's put things in the order that we cover. I mean, we do cover, kinematics first. So what matters next term? Yeah, calculus then. So some of the taking derivatives and integrals, the kind of things that that you might remember doing in physics 4a, you will also do them in 4b. Yeah, basic integration. Yeah. Now the recap, I don't think it didn't mention basic integration, but it's bringing this up. Yeah, vector components. Yeah, Newton's law in dynamics. Yeah, forms the template. Yeah, we call this Lorentz force law. We'll introduce it part by part. We'll do charge times electric field first, and then modal equations. Self-check. Can you set up it? Yeah, so we did that for oscillator. Now the damped oscillator, most of the instructors don't cover that. I do cover it using complex exponentials. And then energy methods, yeah. And potential energy. Doesn't mention voltage, but I think it might be fine. Conservation of mechanical energy, yeah, generalized to this. So yeah, so this is good enough of a summary of what's been covered. Now, if it's simply a matter of having something like this available, I could have given that to you as a handout. But the difficulty that someone could be facing is that looking at the summarized handout, maybe much of it still doesn't make sense. Yeah, and then here's how to turn this into a review plan. There's a triage. Glance the 8 headings, circle anything that feels fuzzy, single page reviews, each circle the topic, condense, yeah. So let me, and this is something that you can do on your own. Now, taking it from here, you could spend some time, one weekend, doing this review yourself. But if you wanted help and somehow I'm not available, then this is the kind of thing you can ask generative AI, like here. So let me imagine that I feel fuzzy on rotation. In fact, let's say this is one of those weird symbols that I have no idea what that means. So I feel fuzzy on rotation and angular momentum. In fact, the quantities you have under rotation column, I'm not even sure what they are called. Are they letters? Can you help me review and practice rotation and angular momentum? And it might describe those Greek letters, give you the names of the Greek letters like omega so that you can search, although, here you could have just copy and paste. Like, this omega, you can right click, copy, and paste the Google search. It'll come up that it's called omega. Yeah, and it knows my name because it's in its memory. It knows I'm called Andrew. Although, I don't know how my ChatGPT's opinion of me is. Oftentimes I am role-playing a student who's lost, so I don't know if it thinks I'm lost with the physics or if I'm good with the physics. Don't know. So I could have asked for single-page review sheet, so for more detailed review. Oh wow, it gave me these images. Are these actually correct? I'm not, no, I think it's coming from, yeah, so, because the ChatGPT, as far as I know, cannot generate correct diagrams yet, but it's able to find these images that are relevant, and I think they look correct enough, or relevant enough anyway. And decoding the rotation alphabet, yeah. still not giving you what they are called. Yeah, but you know what the symbols mean. Great. These are so it can go into more detail that a static review sheet won't be able to do. Let me see. Yeah, so it can give you some multiple choice questions. By the way, you will see lecture comprehension questions that I generated with the help of ChatGPT. I do review for correctness and kind of being at the right level, so it can give you these self-check questions, and you can actually try it on your own. And then if wait, I guess it did give you an answer. Now, if you wanted to expand on an explanation for this, you can ask. It's the kind of wonderful thing that generative AI lets you do. Have basically a virtual tutor who's immediately responsive, available. So, yeah, challenge problem. So this is what I would say is now available to you with the wonderful technology that's become available in the last couple of years. So coming back to the slides, that's how you might prepare for this semester. Now, in this video, we are going to work through 5 different sample homework problems from Physics 4A, touching on a few different problem-solving techniques you have learned in Physics 4A. They cover kinematics, circular motion, with what we call standard strategy for force analysis folded in, energy, oscillation, and a second example using conservation of energy. Do please take a look at this video and the mechanics review problem set to test for yourself how much review you need. I encourage you to try asking ChatGPT questions similar to what I was just asking for more in-depth review. And at some point, please make sure to get started in the thermodynamics material we are also covering this week. Let me do the first question because it's kind of a generic problem solving question. It's a bit independent of what specific topics we are covering in this class, because one of the skills that we hope student you develop as you go through a physics class is a quantitative problem solving skill. And good aspect of kinematics kind of works out that way, because it's the skill you're developing is about reading English description of a setup and kind of understanding enough of the setup to develop mathematical description of that setup, and then use that mathematical description to work out any quantities that you need to work out. So let me demonstrate that with this. So it says marble rolls of a tabletop 1.25 meter high. I like to draw kind of figures as I try to figure out what information the question is giving me. So that's what I'm drawing. Marble is rolling off a tabletop of a certain height. And it hits, and I guess it's gonna kind of go through like a projectile motion thing. And it'll hit the floor at a point 3.9 meters away, or distance d away from the table's edge in a horizontal direction. All right. So it asks, how long is the marble in the air? And I hope in Physics 4A you learned kinematics equations, especially the kinematics equations for motion under constant acceleration. And you remember expressions like this: the height of an object falling under gravitational acceleration is -1/2 gt squared plus initial y velocity t plus initial y position. And it's the there's a lot of synthesis to be done, where you have to bring in the things that you know, kind of understand at an intuitive level that it somehow relates to questions like this,
you kind of, it's, like in the Hitchhiker's Guide to the Galaxy, there's a, what's the answer, the ultimate answer, and the harder part is coming up with the ultimate question, and um, and that's really the harder part in physics, coming up with the equations that you have to solve in order to actually go through the math. And that's the skill that we hope that you developed as you worked through Physics 4A, and that's the skill that we hope that you continue to develop as you work through Physics 4B. So I know from having gone through Physics 4A that this equation is somehow relevant, and having written it down, I know it simplifies because the initial y velocity is 0. It's only moving horizontally. This is just the x component. And for the how long marble is in the air, so I'm looking at the point when the marble hit the ground. So say that this is t equals 0, and I'm looking at when it hit the ground. So at that time, t final, I know the y position of the marble should be 0. It should be on the ground. And my initial y position is h. So that gives me the equation to solve for. Let me write down the simplified version here. 0 is equal to minus 1/2 gt final squared plus h. So the rest is algebra. And this algebra is not complicated. The complicated and difficult part is actually coming up with the equations themselves. Because in many of the physics questions, you're not told what equations to use. You are expected to know what they are from your understanding of physics. So let me solve this for T final. I'm just going to do that in my head in the interest of time. 2h over g square rooted. And I'm just going to check the units. This should be in the unit of seconds, and this should be in the unit of meters. Meters per second squared, meters cancel out. This goes to the numerator, square root. Okay. So the units work out, so I probably did it correctly. So yeah, so, and you plug in the numbers, and that'll give you the answer there. Let me keep working through. So it asks, what is the speed of the marble when it leaves the table's edge? So I labeled it here, but I guess reading the question more carefully, I realized, oh, I was never told what this is. So that's a label of an unknown. So I need some additional information to figure this out. And this is where, you go through the equations that you know, and one of the equations that hopefully you will hit upon as being relevant to this question is one that relates the displacement with speed and time, which is that displacement is given by average speed times the duration of the movement. Here, if you go back to the projectile motion, the x component of velocity is going to be constant. So what I labeled as the average velocity really is just the initial x velocity. And and I worked out the time here. This duration of time is this t final that we worked out earlier. And the delta x, the displacement in the horizontal direction, we are given that here, so d. So let me solve that for v. That should give me the what they are looking for here. So this was A. For part B, all I need to do is to solve that for speed. Initial x velocity is the displacement, d, divided by the time, or let me just write that out, square root of 2h over g. And I guess I just had to plug in the numbers. All the numbers are given. And what is its speed when it hits the floor? That's where you kind of have to recall vector quality of movement. So you have, so when it left the table's edge, this was the entire velocity. It only had the horizontal component. When it's hitting the ground there, it has, it's moving in a kind of diagonal direction. So it has x component, which will be the same x component that you had before, v naught x. And it'll have downward direction, which is v naught y final, that you kind of have to work out. And once you work this out, then the final speed will be given by the Pythagorean theorem, square root of the x component squared plus the y component squared. So I need to work this out. And for that, I recall one of the kinematics equations, which is that the v final is equal to v initial plus acceleration times time. In this particular case, in the y direction, acceleration is minus g. So this will be v naught minus gt final. The v naught was 0, so go to 0. So I have t final from part A. Many physics questions are kind of cumulative. That's why it's good to organize your work, because you might need it. So yeah, so I plug this in. Then I get for that v naught y final is equal to minus g times that quantity there. And doing the simplification in my head, it's 2h square root of 2hg. And at this point, I'll probably just plug in the numbers and use those numbers to calculate these to get the speed for part C. So yeah, that's the kinematics question. And the intent of this mechanics review problem set is that, this kind of have you recalling a lot of things that you learned in physics 4A, and it's been a while that you might have forgotten. And the intent here is that it's a space for you to kind of review for yourself. There isn't a great stress to get everything. It's all extra credit. I hope you'll get 100%, but if you don't, no big deal. I'm kind of more anxious to start out with the physics 4B material, but I want you to provide this space for you to do this review on your own. So even though this is not the question that I thought it was, I think it's still worth going through. And really the reason for it is it involves centripetal acceleration. And of the many different things you learned in physics 4A, one thing that we will use in physics 4B is centripetal acceleration. We probably won't use any of the whole projectile motion thing. Like, there are no projectiles in that occur naturally in physics 4B, so we won't really use the projectile motion thing. But one thing that will come up is the centripetal acceleration when we do magnetism. So I think this question is worth going through. So let me do that. So so this is so let me just read the question and draw figures as I'm reading the question. That's kind of my process for making sure I understood all the information in the question and that I didn't miss anything. So it says 30-gram ball at the end of a string. So I'm drawing a string and a ball at the end. And it says it's being swung in a vertical circle with a radius of some radius r. So this is the trajectory of this ball. Oops. Let me finish drawing it and move it down. The tangential velocity is v. Find the tension in the string at two different positions. So I drew one already at the bottom of the circle. So this is going to be b. And I guess I have to consider when this is at the top of the circle. So no, that's the center. Let me draw the radius. That's the radius. And it says find the tension in the string. So what is the tension T along the string? So as you read it and stare at the questions, this is the first thing you have to realize as you are
considering this question, that this is a Newton's law problem. And this is my biggest hint that this question involves Newton's law. It's that it's asking for tension, which is a force. So I'm looking for a force. So I should use a problem-solving strategy that involves forces. And that's Newton's law problem-solving strategy. There are sometimes other hints you can look for. If question somehow involves a finding acceleration, there's a chance that it also has to involve net force. So here I see that it's asking for tension, which is a force. So I have to use Newton's law problem-solving strategy to find the tension. So this is a quick review of Newton's law problem-solving strategy. In my physics 4A class, we call this standard strategy. You go by 4 steps. So let me actually lay out those 4 steps. Different classes might kind of label them differently, but I hope you recognize the element of what you learned to do. So in Newton's law problem-solving strategy, you start by drawing free body diagram. It's free body diagram is a diagram that's part of the problem-solving toolkit. It allows you to label all the given information and make sure you didn't miss anything. And it's a diagram where you lay out all the forces. And once you've drawn free body diagram, then you have to define coordinate axis. And when you define coordinate axis, you usually do it so that one of the axes, let's say x, is parallel to the direction of acceleration. And I don't think this will come up for this question, but for most 2D problems, you have to decompose the forces. So you have to break down the force vector into x and y components. And these steps kind of one leads to the other. So in step 2, you have to define the coordinate axis so that you know what the x and y directions are. And once you've decomposed all the forces into x and y components, then you should have everything laid out in the free body diagram in a way that allows you to the 4th and the final step, which is writing down the Newton's second law equation. Net force is equal to mass times acceleration. And for 2D or 3D problems, this is actually multiple equations in one. For 2D, it would be net force in the x direction is equal to mass times acceleration in the x direction, and net force in the y direction is mass times acceleration in the y direction. And if you did step number 2 correctly, then this should be 0. Now, here's one reason why reviewing Newton's law problem-solving strategy is useful even at the beginning of Physics 4B. Because I'll tell you right now, in Physics 4B, we are not going to be using standard strategy that often. Because it just, Newton's law problem doesn't come up that often. But what this is useful as is that this is a model of systematic problem solving. This is the thing that students struggle with the most in physics. Students are so often looking for the equation to use, what formula to plug in numbers into. And in all but the easiest physics problems, you just don't have that. The hallmark of a physics problem is that there is no single simple formula that you just plug in numbers into. It's an entire system you have to analyze. You have to come up with your own equations that you write down, and then you simplify it, and then you finally have a formula that you can plug in number into. But working through that, deriving the formula, that is the big chunk of physics problem solving. So the Newton's law problem solving strategy is good as an example of how that's done. And you will see other examples in Physics 4B, and I hope you kind of draw some similarities as we go through those new strategies. So let me work through this question here. So I'm gonna, I'll just go in order. I'll do part A first. So I'm doing it for the top of the circle. So I'm kind of taking this picture here. This is the picture I'm looking at. I should start out with a free body diagram. So when I draw a free body diagram, I try to keep it as simple as possible. I use a dot to represent the object. So this is the object of mass M. So, and I identify all the forces. And this is the part that should take the most amount of thinking, care, because if you do this wrong, then the rest of the steps are messed up. If you do this right, then the rest kind of follows through mechanically. So when I'm drawing forces, I like to draw only the forces that are necessary, that I know has to be there. One force that I know has to be there in this case and almost every case is there has to be gravity. So let me draw gravity as a force, mg. Looking at this picture here, I see that there should be one more force. There's this string that's touching the ball. So it must be pulling on the ball. So there should be a tension force that's pulling the ball down. So there should be a downward tension force. And then I think to myself, should there be another force? And as I'm thinking to myself and thinking out loud, one of the things that I'm looking at is I should look at and kind of make sure that it makes sense is that these two forces that you see here combined represents an acceleration that's downward. And I need to be okay with that. That downward acceleration makes a sense for this snapshot. And depending on how well you did in physics 4A, it might take a little bit of time, maybe not. And eventually it should make sense that, yes, you should have downward acceleration here. This is going to be your centripetal acceleration. Because this ball is moving in a circle, it is always undergoing centripetal acceleration. So up here, it's centripetal acceleration points to the center here. So when the ball is up there, the centripetal acceleration is pointing downward. When the ball is down here for part B, centripetal acceleration will be upward. So the free body diagram I drew, it has to be consistent with this direction of acceleration. And I see that it is, so I'm fine with that. Okay, let me move on to step number 2. I have to define coordinate axis. I found my direction of acceleration, so let me make that my direction of the positive x-axis. Okay, I don't need to decompose any forces. Everything is along the positive x direction. So all I need to do is step number 4. I need to write down the Newton's second law equation. That net force, which is tension plus mg. Oh, by the way, tension at top because part B is going to be different. That's equal to mass times acceleration. All right. So that's the end of what we call standard strategy. And this is a good point to kind of stop, see what you know. So the goal of Newton's law problem solving strategy is to reach this point, which isn't actually the answer because it's a general problem solving strategy. The strategy doesn't know what question was asked of you, but the goal of the strategy is to get you to a point where whatever the question is, you are in a place to answer it. And that place to be is to have a system of equations in which you can identify knowns and unknowns and solve for the unknowns. So I have my system of equations, system of one equation, where I hopefully have only one unknown, but let's see. Let's count all the knowns and all the things that I don't know. Now, I don't know the tension. That is the question I'm trying to find it. I know the mass. I was given the mass here. I know G. I mean, I wasn't given it, but I remember G should be 9.8 meters per second squared. And the mass, I know that already. acceleration. Was I given that? Now, as I look at the given information, radius and velocity, I don't see acceleration. And this is where it's helpful if you remember something about centripetal acceleration. Because in physics 4a, you are given a formula for centripetal acceleration. That centripetal acceleration is equal to the tangential speed squared over the radius of the circle that it's moving. So I'm not given the acceleration directly, but I'm being given acceleration in terms of these two quantities which are given. So let me go just one more step here and just to rewrite this as m times v squared over r. Now I have one equation in terms of one unknown. So I just solve for that one unknown and I'll be home free. Tension at the top is equal to, let me move that mg over. So I have mv squared over r minus mg. Is that right? Yeah. So there's a minimum speed v at which the tension will be 0. And as the ball moves faster and faster, tension has to be greater to so that I think all that makes sense. Yeah, so that's the answer. And to actually answer the homework question, you do not have to plug in the numbers. When you are plugging in the numbers, this is one thing to be aware of about the MyOpen Math questions we use in this class, which is that they are all programmed in with default tolerance of 1%, which means you need to keep a minimum of 3 significant figures to make sure that you don't get rounding errors, which result in the system telling you your answer is wrong when it's kind of right. So, keep 3 significant figures, then you will get an answer that's should be graded as correct if it's actually correct. Okay, let me speed it up here and actually finish answering part B. At the bottom of the circle, so it's the exact same process with some minor details changed. So
I'm sorry, I have a question.
Yeah.
So in the part A, in the free body diagram, so you draw force, the tension and the mg downward, and then the acceleration also downward. So which force will keep the ball not falling down?
No force. The ball is accelerating downward. It is accelerating downward. There is no upward force here at all. Does that answer your question? Let me rephrase the question. I think when people ask what keeps the ball from falling downward, this is how I'm trying to parse your question. And Min, thank you for asking that question, because this is kind of the work that is done in physics 4a. It's not, and this is the work that takes a long time to actually to get done, because it has to do with realigning your intuition so that what you intuitively expect aligns with the equations that we write down. And here, what you are kind of intuitively seeing and expecting is that as you spin the ball, one thing that you see is that the string remains taut. This string that you see here, it remains taut, straight when the ball is at the bottom. And when the ball is at the bottom, that the string remains taut, that seems reasonable. No one's having any issue with that. When the ball is at the top, now if you simply release the ball from there, then the string will go slack. So what you are used to seeing is that as you're spinning it, the string remains taut. And at least when I hear people ask, what keeps the ball from falling down? What you really mean to say in a mathematically precise way is what's keeping the string taut. And what's keeping the string taut is the fact that tension is greater than 0, or that it's a non-zero value. and string can only pull. So this tension can only be in one direction. It can only be downward. So what really keeps the string taut is that this acceleration is greater than g, because g is when it's in free fall. That's when the string will start to go slack. That's when this and that condition is met when the v is so small that this v squared over r is exactly g. That's when the tension is 0. As long as the speed is greater than that, the centripetal acceleration formula says the acceleration will actually be greater than g. And in order to make the ball accelerate downward faster than it would under free fall, tension has to be greater than 0. Hopefully that answers the question. If not, ask a follow-up question. So, and I think I say this to my Physics 4A students, that Physics 4A is the hardest physics class. It's even harder than Physics 4B. And part of that is that a good chunk of the work you are doing, or you are supposed to be doing in Physics 4A, is realigning your intuition, kind of refining your intuition so that what you are used to expressing in imprecise language, you learn to express in more mathematically precise way. So anyway, so that's part A. Part B, let me go through this a little bit more quickly, and it's actually also a little bit easier too. And so let me go through this a little bit more quickly. The free body diagram looks like this. It has gravity still, mg downward. And there's tension, and this time it's upward. And yeah, I guess. So here, if one were to ask the question, what's keeping the ball from falling down, we can honestly say that it's the tension. Now, what's important to know here is that tension will actually be greater than mg. So with this particular free body diagram, acceleration can actually be 0, and that would be the case if this velocity were 0, then acceleration will be 0, tension will be equal to mg. We don't have that. As we drew here, when the ball is down here, the acceleration should be upward. So here you actually have upward acceleration, so tension has to be greater than mg. So that's step number 1. I drew free body diagram. Let me define my coordinate axis. I'm going to define upward as my positive x-axis. Nothing to decompose. Now I can write down my net force equation. I like to write down my net force equation in a way all the symbols are positive and the signs are in the equation. So with that convention, my net force would be tension, positive, minus mg. So that my m and g are positive, but it's opposing tension. That's equal to mass times acceleration, and I learned from doing part A, acceleration is a v squared over r. So it's mv squared over r. So, this is tension at bottom. So this is the end of the standard strategy. I have this system of one equation in terms of one unknown that I'm ready to solve for. So let me solve for that. I get tension at the bottom is equal to moving mg over. I have mv squared over r plus mg. So tension at the bottom is greater. It's at minimum mg, and depending on whatever the velocity is, it's going to be greater. Okay. All right, let me do this question here. So I think I pulled this question out because it deals with energy. And thermodynamics, a good chunk of it is about energy and conservation of energy, at least in the conceptual realm. So he says a small block of some mass, let me give it a symbol, M, starts out at rest point A, slides to B, where I'm given its speed, VB, then slides along the horizontal surface a distance of 10 meters before coming to rest. Let's see. All right. It asks, what is the work of friction along the curved surface? So this is where I hope you start thinking in terms of energy conservation, not in terms of forces, not in terms of kinematics. One thing that should really encourage you to do that is the fact that this is a curved surface. If you try to, one, you're not given enough information to actually do any detailed force analysis. Two, even if you were, it will get too complicated. It's much better if you can somehow work this out on the basis of conservation of energy. So, that's kind of the starting point. With the conservation of energy, it's useful to look at snapshots. So I have this snapshot here at point A. So here, I think I actually know the expression for total energy. The total energy at this point, which is going to be potential energy plus kinetic energy. But I know kinetic energy here should be 0 because starting from rest. So my potential energy is just going to be gravitational potential energy. Oh, let me give this a label, H. So my starting energy at point A is going to be mgh. That's my energy at point A. So, and by doing that, I kind of implicitly set this point to be y equal to 0. So when I look at the second snapshot here at point B, my gravitational potential energy will be 0, but I'll have kinetic energy. So I'll have kinetic energy that's going to be equal to 1/2 mvb squared. And now I hope you have enough intuition about energy, enough intuition about mechanical energy from your physics 4A here, which is that the moment they mention the friction, you should realize, oh, mechanical energy is not going to be conserved. So the total energy at point A and the total energy at point B, if there were no friction, these two would have been equal. But because there is friction, they won't be equal. Instead, there will be a difference in the total energy. There will be a change in energy, which I might define it as total energy at point B minus total energy at point A. And this change in energy, and this is another thing that hopefully you learned at an intuitive level from Physics 4A, which is that whenever there's a change in energy, for the agent that's causing the change, you are looking for work done. Work is what changes energy. Work can be expressed in two different ways. There's the definition of work, which is the force dot product of displacement. That's one. But the physical meaning of work is that it causes energy to change. So here, all this change in energy, we are blaming all of that on friction. So this is going to give you the work done by friction. So once you get that, then the rest is kind of just writing out the expressions. So the work done by friction should be the total energy at point B, which is 1/2 mvb squared. 1/2 mvb squared. You have all the numbers for that mass here, converted to kilograms, by the way, minus the total energy at point A, mgh. Now, when you plug in all these numbers, you are actually going to get an answer that's negative. And that's perfectly fine. That's in fact what the question here expects you to have, a negative numerical answer. And the physical meaning of that is that the work friction is doing is reducing the mechanical energy, specifically kinetic energy. So you plug in the numbers, you get a negative answer, plug in the answer here with the minus sign, that should be all that's needed. Okay, so with that so part B is similar to part A. It just takes one additional step. So
Sorry, I have a question on part 8.
yeah,
Um, do we have to calculate the work of friction from B to C?
no, because it says along the curved surface, so it's just A to B. Good.
Okay, thank you.
Yeah. Yeah, if it's all the way to C, then it'll be too easy because it's basically this entirety is conduit to friction. So, yeah, but along the curved surface, so it's just A to B. Now we do B to C. That's what part B is asking. That's what part B relates to, because the part B is asking, it's kind of asking in a sneaky way, because it looks like it's asking for the coefficient of kinetic friction. And if you focus on that, start looking up formulas for coefficient of kinetic friction, you're just going to get lost. Even though it's asking for coefficient of kinetic friction, the place you have to start from is conservation of energy again, or at least energy considerations again. And starting from that, I'm actually going to be using this at some point in the steps. And then I'm going to be finally using the expression for kinetic friction force. But the starting place here, the natural good starting place has to be consideration of energy. So here, the total energy at point C, that's kind of simple. You have zero speed, zero potential energy, so zero. So the change in energy as you go from B to C, and let me make this easy for myself. I'm just going to look for absolute value so I don't have to deal with the signs. That's simply going to be whatever energy you had at point B, which is 1/2 mvb squared. All of that energy is reduced to zero due to the work done by friction force. Now, this is a part of the physics problem solving, which is that you try to connect what you know with what you are being asked for. And so I want to relate energy to coefficient of kinetic friction. And if you're looking things up on coefficient of kinetic friction, the context where it comes up is the kinetic friction force, which is the coefficient times the normal force. So, so I can, if I have a kinetic friction force, through knowing the mass of the block, and in this horizontal plane thing, this n here should be mg. I mean, n is not always mg, but in this case it is. So once you have kinetic friction force, you should be able to relate it to coefficient. So then now my focus moves on to relating the energy to the kinetic friction force. And that's where it's good to remember the definition of work. Work is defined as force times displacement. And as the block moves from here to here, displacement is going to be 10 meters there. This is my delta x. And the friction force will be doing negative work to cause this amount of magnitude of energy change. So let me kind of write down that relationship here. This amount of energy change, it's going to be related to work done by friction force. Again, absolute value so that I don't have to worry about signs. And this work done by friction force, I can use this definition of mechanical work. It's going to be the friction force times the displacement, the delta x. And I'm just going to plug in positive values for both of these so that I get what I would get with absolute value. So, okay, let me write out this right-hand side in place of the kinetic friction force, and I think I'm going to be ready to solve for the coefficient. So this is going to be mu k times mg times the displacement. Now, when you look at this system of equations, this is the left-hand side. equal to this right-hand side, you see that you have one equation and one unknown, just the coefficient. So solve for coefficient and you should be done. In fact, I think about doing that, m actually cancels out, so I didn't even need to know the math. I mean, I know it, but I didn't need to. So let me solve for coefficient. The coefficient of kinetic friction is, let me move g and delta x over. It's going to be VB squared over 2g delta x. Plug in the numbers, that should give you the coefficient. If you want, you can kind of do the unit check. The unit on the numerator is a meter squared per second squared. Unit on the denominator, if you work it a lot, it should also be meter squared per second squared. Coefficient of kinetic friction is a unitless quantity, so you should get something unitless. Good. So yeah, it's a kind of practice on using energy for problem solving. You're gonna see, energy is gonna come up throughout the semester actually, because even when we do electricity, electric potential energy becomes an important thing to consider. There's a kind of saying that the conservation of energy and conservation of momentum are the twin pillars of classical mechanics. And almost in any question, kind of thinking in terms of energy and momentum is going to be useful. Momentum not as much this semester, but energy definitely. I'll do this quickly. I kind of pulled this out as an example of, how do I say, as a counter example for the saying attributed to Lord Kelvin, who said all science is either physics or stamp collecting. If you never heard it, well, you heard it here first. And what it means is, in many branches of science, there's a kind of, where a lot of the activity is a collection of facts. And what we physicists pride ourselves over is that in physics is fundamental science, we try to learn things at their very basic level. So we don't memorize a bunch of formulas. We try not to memorize a bunch of facts. So that's the kind of default mindset in physics. I call this counterexample because the best way to do this question is to have memorized a bunch of formulas. So it's, this is a mass attached to the spring. It's a simple harmonic oscillator problem. So if, this is what the diagram will look like. I have a mass attached to a spring, attached to a wall, and this spring has some spring constant, and this mass is going to oscillate back and forth. And you should have covered this towards the end of last like 2-3 weeks of physics 4a. And what you should remember from that coverage is that when this thing oscillates, it oscillates at a natural frequency. And the formula for that natural frequency of oscillation, this by the way is omega, Greek letter omega, it's not W. The natural frequency of oscillation is the square root of k over m. I mean, you can drive it by solving the equation of motion and going through all the differential equation stuff. You can do it, but it's the kind of the standard way to do this is to have memorized this as a formula. So that's kind of what you needed to do. And to answer part A here, the easiest thing to have done is to kind of have memorized a bunch of formulas and expressions. One of them is a kind of equation for the displacement. When you have a simple harmonic oscillator as a function of time, it'll move the amplitude times sine or cosine, either is fine. I guess I'll use sine here. Sine of omega t, where the equilibrium position is x equals 0. So this is x equals 0. And the velocity is also given by Vmax times, well, let me do absolute value of velocity. Absolute value, here it's gonna be cosine of omega t. And what you should know, and I guess this is a more physics-like part, which is that the velocity through kinematics, it's related to position by the derivative. So you can actually see how this relates to this coefficient here, Vmax. When I take the derivative of that expression there, I get a times angular velocity, also a natural frequency of oscillation, times cosine of omega t, which means this is equal to the Vmax that's given there. So you have everything you need to solve for this. Solve this for A, that's your answer. So your amplitude is Vmax divided by omega, where omega comes from this formula. And the period, that's another formula you had to memorize, having to do with anything that's a periodic. There's when you are covering oscillation, there's a kind of few related quantities that you had to know. One kind of starting point is relationship between period and frequency. Period is 1/f. And the other is the relationship between frequency and angular frequency. Angular frequency is 2 pi times frequency. And believe it or not, this, or believe it please, this 2 pi is doing a unit conversion because, well, quote unquote unit conversion, because the frequency is given in terms of cycles per second, and angular frequency is given in terms of radians per second. And this radians will be phase angle in this case. But in any case, this 2 pi is converting from cycles to radians, because one cycle, there are 2 pi radians in one cycle. Anyway, so these are the, once again, formulas that you kind of just have to have memorized. And once you have that, then you can see that period is, so f is omega over 2 pi. So period should be 2 pi over omega. I have omega there. Oh, I have k and m. So once I have omega, plug it in here. That'll give me period in seconds, because this 2 pi already did conversion from radians to whatnot. And C and D, I'll just give you the answer. C, it should be 0. I don't know if there's a lesson that's relevant here for physics 4B. I mean, it's that when it's at maximum speed, it's at equilibrium position, and equilibrium is defined by having net force equal to 0. If you have 0 net force, you have 0 acceleration. And what is the magnitude of acceleration of the mass when the speed is 0? That takes a little more work. I think the easiest one, surprisingly, is to kind of do a little more calculus. So you have this expression for v of t, and you know from calculus that acceleration is given by the derivative of velocity. So I can just take one more derivative of this. That will give me, using the chain rule, I get minus a omega squared times sine of omega t. And this coefficient here, that's my a max. That's the acceleration I get when sine of omega t is 1, meaning the mass is at the maximum displacement. And you can also do it the other way. You know the maximum displacement, and you can use a Hooke's law, and you can do that. That's fine. That'll give you the same answer. It just takes more steps. So I pulled this out as an example of sometimes they're just the formulas to memorize, and you will actually see some questions like that for problem set 2. I think there's a question about Stefan Boltzmann law. It's a radiation law. There's a formula for that in your textbook. You just have to know it. I mean, in physics 4C, we are gonna cover black body radiation a little bit more, but yeah, there are some aspects of physics where sometimes you just have to have things memorized. So this is another energy question, and I think a part of the especially is one where it'll give you some practice for kind of general problem solving. This is the skill that we are trying to develop in all physics classes, which is that you hear a description of a physical system, you think through it, you come up with a mathematical description of the system, and part of that mathematical description somehow boils down to a system of equations, which then you can solve algebraically to find the answer that you are looking for. And that's what you will be doing in D, and that's a kind of the question like this where if someone asks me, oh, what formula do I plug in numbers into? My answer is, there's no one formula. You just have to go through the steps to actually find the formula yourself. So let me start this here. It says an object of mass m is released at point A. So it's starting out at equal to 0, slides to the bottom. So at the bottom here, it's moving at some speed, collides with a horizontal massless spring, compressing the maximum distance of 0.75 meters. So let me imagine this is where the maximum point of compression is. The distance was 0.7, or give it a maximum distance it compressed was D. And this is M here at that point. Now, the thing about the maximum compression is that at that point, speed is equal to 0. Because if it's not, then it will either be compressing more or it'll be on the way out. So at the maximum compression, speed is 0. That will help us when we figure out the energy terms. The spring constant is given, and the height of the incline is some height. And the horizontal surface is frictionless. Oh, so there must be some friction here. I mean, I'm just, there's a principle, it's kind of pointing out one thing is to, at the same time excluding the other things. If they are saying the horizontal surface is frictionless, that must mean the non-horizontal surface is probably not frictionless. So I'm going to assume that this incline has friction. So, oh yeah, so when it asks what is the speed of the object at the bottom of the incline, so one thing I'm not going to be using is energy conservation from point A to, let me label my points. One thing I'm not going to be using is energy conservation from point A to B, because from this hint here, I have a sense there's friction here. So I think I know energy won't be conserved on the way down. So I won't use energy conservation along that step. What I think I can rely on is everything happening here conserves energy, because conserves mechanical energy. It's a frictionless incline, and there's nothing else. There's no kind of completely inelastic collision. I don't see anything here that would dissipate mechanical energy. So I'm going to use conservation of energy within this box. So I'm at state B, going to state C here, energy is going to be conserved. So I can say total energy at point B is equal to total energy at point C. This is, by the way, the kind of the starting point for applying any conservation law problem solving strategy. You identify the conserved quantity and you start out with the equation that asserts the fact that this conserved quantity is conserved. So that's my kind of symbolic statement for that. now I have to write out all the terms. The energy at point B, it's just going to be the kinetic energy, 1/2 mvb squared, and nothing else, is equal to, at point C, there's going to be a spring potential energy. So spring potential energy, I kind of remember the formula from physics 4a. It's 1/2 spring constant times whatever displacement is squared. At point C, it's at this maximum displacement d. So it's going to be 1/2 k times d squared. And normally there would be kinetic energy, but I already worked out that kinetic energy at that point would be 0. So this is my conservation of energy equation. It looks like I have only one unknown and everything else is known. Mass is known, spring constant is known, d is known. Yeah, so I can just solve this for the speed here and I can just plug in the numbers. VB is equal to, I'm gonna go fast just to do this in my head. Cancel out the 1/2, move m, take the square root, then it's gonna be d times the square root of k over m. So that'll give me the speed and that'll be it. By the way, once you have A, you also have C, because C is describing, okay, the spring pushes the thing back and sends the object back towards the incline. So I guess that would be like the B prime, where it's now about to move up the incline. And within this entire box, energy is conserved. So when M comes back to this point, it should come back to the same kinetic energy it had before, which means the speed here should be the same speed of VB that you calculated earlier. The velocity is different. It's in the opposite direction, but speed is the same. So let's do B and D. B is a little bit easier because we just have to work through the energy differences. And having done A, I think I know all the energy terms. D is going to take a little bit more work. So let me do B first. So I'm back to the thing I was dealing with in a different problem earlier, that I have so at this position here, I have total energy at point A, which just gonna be mgh, gravitational potential energy. And at this point here, I have total energy at point B, which, by the way, happens to be equal total energy at point C. And I think I might just use that instead. And from A to B, there's going to be change in energy. And this change in energy, I can blame that on the work due to friction. So let me write that out here. Change in energy going from A to B is going to be the total energy at point B minus total energy at point A. And because the total energy at point B is equal to total energy at point C, I'm just going to use total energy at point C, 1/2 kd squared. I mean, I could use this, but I prefer to use this because this is in terms of all the known quantities. So in some sense, it's simpler. If I somehow made a mistake in working out VB, this is not affected. So anyways, it's more of a personal preference than requirement. Minus the gravitational potential energy, mgh. And that's gonna be, I'm gonna blame all of this on the work done by friction as this thing slides. So I'm gonna say that's work done by friction. And I think I have everything to just plug in numbers to. And here, as we do before, if you plug in numbers, you will find that the work done by friction is less than 0. That's fine, that's totally expected. It's because the friction force is reducing mechanical energy here. So you should find the negative answer. That's what you should plug in here to get your answer. Now, part D is where you have to think through, kind of develop your own equations and mathematical descriptions and kind of set up your own new system of equations and solve it. I can tell you what the answer will not be. The answer will not be this original starting height. It's because you have friction, and the friction does negative work while this is sliding down, and it also does negative work while it's sliding up. That's the thing that makes friction not conservative, because while this is sliding down, the friction force is opposing that motion, doing negative work. And on the way up, while this is sliding up, friction actually points downward, doing negative work again. So, so whatever height the block reaches, it'll be something a little bit less than 2 meters. So that has to be your starting point. And now we just have to figure out. So what would be nice to have here is knowing that friction force is what we blame for mechanical energy not being conserved. It would be nice just knowing what the magnitude of the friction force is, because that'll give me some handle on calculating how much change in energy there is to account for that on the slide back up. So what I see here is what I worked out in part B can be used to figure out the magnitude of a friction force. And the reason figuring that out is useful is that magnitude of friction force, kinetic friction force, is given by the coefficient times the normal force. And the coefficient is going to be the same both directions. And the normal force will also be the same both directions. It's a normal force, that's the component that opposes this component of gravity. So, so if I figure out the magnitude of friction force on the slide down, that's going to be the same magnitude on the slide up. So I can write down some kind of expression for this much distance traveled, this much energy is lost. So let me figure out the magnitude of friction force. And what I can use there is this here, work of friction on the object, which I figured out some answer to. And I can relate that to the friction force using definition of work, which is force dot product with the displacement. And if we do that, it's gonna be all negative numbers all there. So, so let's deal with the absolute value. That's gonna be equal to the magnitude of friction force times the displacement. And you have to be a little bit careful with the displacement here. It's gonna be the displacement along the incline. So that's worth, I guess this is one of those special right triangle. So, if you just want the numerical value, that should be 4.0 meters. Or if you want the actual correct expression in terms of h and the angle, that's the hypotenuse. So let me label that L. So L over h is equal to sine of theta. It's getting too late. H over L is equal to sine of theta. So if you solve for L, that's gonna be, or this delta x is gonna be h divided by sine of theta. Here sine of theta happens to be 1/2, h is 2, so L is 4. So all of this, I think, gives us enough information to write down an expression for the magnitude of friction force. So magnitude of friction force is equal to whatever that work was, which I figured out the answer to, divided by the length of the hypotenuse, which would be h divided by sine theta. So that's the magnitude of friction force. And using that, I can now kind of think through this process. Let me clear up some space here so that I can write out what that process is. So when I do problem solving, especially new problems I haven't seen before, something new, I'm kind of deriving entirely new formulas. what I like to do is think sequentially, kind of visualize what's happening in real time. So this is moving up with some V, B, and as it's moving up, it's slowing down. It's slowing down actually for two reasons. It's slowing down due to gravity, and it's slowing down due to the friction force. Gravity will conserve energy, so to some degree, I don't have to worry about it too much. Well, yeah. Friction won't conserve energy, so I have to take extra care to account for the work done by friction. Now, as this is sliding up, it slows down, eventually comes to a stop somewhere at a point lower than height of 2 meters. So let me call that point, I don't know. Let me call that point x final. So this is going to be one of my parameters for describing this physical situation. So I'm going to use energy conservation still. At this point here, I'm going to have total energy at point B, which is, this energy here. That hasn't changed on the way up. That's the energy I'm starting with. And this final stopping point, this is going to be a new point. Let me label it D. And there will be some total energy at point D. So I need to write out that expression. So as you go from B prime to D, the energy is going to change. And this change in energy, as you go from B prime to D, is going to be the energy at point D minus the energy down here, which is energy at point B, same as energy at point B prime. And this change in energy will come from work done by friction. And that's going to be negative work. So let me put the sign into the equation, the negative sign, minus times the friction force, magnitude of, just to make sure there's no confusion about if it's friction force is positive or negative. I'm just going to use the positive value times the displacement, which will be x final here. So this is kind of my starting point for my system of equation, and it's going to be system of one equation. The unknown I want to solve for is x final, and I figured out the friction force, so that is presumed to be known. So what I need to do is write out the expressions for the total energy at point D and point B prime. And let's see what we have to solve, what we have to work with from there. Okay, let me just work through this here. The energy at point B, or energy at point D, is just going to be the gravitational potential energy. I need to work out this. So that's the opposite side with the hypotenuse given by XF. So this height here, lowercase h, is going to be hypotenuse times the sine of the angle, 30 degrees or beta. So what I have to do is write down the expression. So that's the height at the point D. Gravitational potential energy is going to be mgh. So that's going to be mg times that height, x final times sine of theta, minus total energy at point B. I'm going to use this expression here because that's the one that has most known quantities. Kd squared is equal to minus times the magnitude of friction force times the x final. So I have two x finals here. So I need to finish the math and solve for the final x position here. So let me quickly do that. I collect the like terms, collecting the like terms. Let me collect the terms with x final on the left-hand side. Then I get mg sine theta plus the magnitude of friction force, and I kind of factored out x final already, is equal to, moving this over to the right-hand side, 1/2 kd squared. So solve for x final, divided by the coefficient there. I get x final is equal to 1/2 kd squared over mg sine theta plus the magnitude of the friction force. So, okay, this is something I can plug in all the known numbers to get x final. Now, one word of caution, that's not what the question asks for. Question is asking for the vertical distance. So I have to remember that this hypotenuse is the vertical distance h divided by sine theta. So once I have x final, I have to remember to multiply both sides by sine theta to solve for h here. So it's a multi-step process. It takes time. It takes thinking through. And when you get it, you'll like it. But this is kind of, well, this is a very typical of a physics question. And this is the part that a lot of people do find it challenging. But once you gain enough practice at it and you are good at it, that will be what you enjoy about physics. Because it's like any difficult thing that takes people a lot of time to learn. It's something that you are able to do that not everyone else can. So